Welcome back to the Distributed Control and Automation Framework video series. Today we'll walk through all the steps necessary to create your own custom plugin for decaf using the simpler of our two module templates, the static channel module template. This is the template to start from if you know in advance how many inputs and outputs your module will have. If you need to dynamically create channels based on editor configuration, for example, reading from an unknown number of input modules via scan engine, you should use the dynamic channel template. For the example today, we're going to recreate one of the existing decaf modules, the LED module. This module is responsible for blinking the LED on a National Instruments real-time target in a user-defined pattern. Pretty simple module, but it does let us see all the details necessary to create your own custom plugins. First, let's take a look at the existing module to understand the different pieces that we'll need to create. If we add an LED module in the decaf editor, we can see what we're about to build. We can add an LED module to an engine running on a compact Rio, so add LED, but we can't do the same for an engine running on a PC. There's no LED here. Why not? We configured the module to not be runnable on Windows targets because Windows targets don't have an LED to blink. Notice when we add it, under the compact Rio, it has the name LED configuration. When we click on that, we get a configuration screen that presents us with 3 channels that we can map to tags or just set defaults, or both. In this case, we have enable, blinks per cycle, and a selection for the color, either green or yellow. So in the most simple case, we could just set defaults here. So I'll just set 2. And I'll set it to be green. At this point, if I was to deploy this configuration to the target, I would get a LED that blinks twice, waits for a little bit, blinks twice, and waits for a little bit. Very straightforward, very simple, about as simple of a logic as we could possibly demonstrate. Notice that a few things that we can't do here. We can't add additional channels to this module. It has these 3 channels and these 3 channels only. Notice also, if I go to the compact Rio engine and attempt to add another LED module, it won't let me. The reason is we configured this module to allow only 1 instance per target. It doesn't make sense to have 2 separate modules controlling the same LED. Now let's take a look at the actual source code of the LED module that's available via the LabVIEW Tools Network VI Package Manager repository. This is what installs on your system when you install the LED package. It might seem like a lot, but it'll make sense shortly, I promise. I'll show you exactly what you need to edit to build all of this yourself. Most of it's going to be provided for free by our templates. So you can see the project. A decaf module is composed of 3 LabVIEW classes. We have configuration, editor, and runtime. Each of the 3 classes in a decaf module's project serves a very specific purpose. The editor class is what provides the user interface for the configuration editor that we saw a moment ago. It's responsible for collecting user input and creating or modifying a configuration class to contain the desired configuration of the module. The configuration class is what gets passed between the editor computer and the runtime target, which are often 2 separate machines. The editor creates the configuration. The runtime initializes itself based on the configuration. The runtime node contains all of the execution logic that the system runs on the deployed system. So editor node runs on Windows, creates a configuration. Configuration is serialized to a text file. That text file is transferred over to the running system, say a compact Rio. At runtime, the runtime node will initialize itself based on the configuration information that it pulls out of the file. An important note here: make sure that you put any type definitions or accessor functions that need to be used on both systems into the configuration class to avoid cross-linking. In the static channel template, we take care of all of that for you. We'll talk much more about this in the video for the dynamic channel template. Now, let's take a look and see what the template itself gives us and what pieces we still need to fill in ourselves. In LabVIEW, to create a module from the static channel template, first click Create Project. Next, you can filter just for decaf templates, or more specifically just decaf module templates. Here you have the choice between the dynamic channel or the static channel templates. And for this example, we're going to use the static channel module. Next. Need to give it a name. In this case, I'll just call it Demo LED. I'll just go on my desktop, just for example purposes. Now here, we have this table which lets us choose the channels that are going to be provided by our static channel module. If you recall, the three that existed on the shipping LED were enable, which was a Boolean. We had the blinks per cycle, which was an I32. And we also had color, which was a Boolean. You may notice that I had to choose a channel type, and there were 4 options there. There was input data, output data, processing parameter, and processing result. And knowing which one of those you want can be a little confusing at first if you haven't seen this. Let's take a look at a slide. An input module is responsible for generating data and putting it on the engine for either itself or other modules to consume later in the cycle. Input methods only push data to the engine. Process methods are responsible for taking data from the engine with a processing parameter type, doing something with it, and providing output data to the engine. So it takes data from the engine and updates information as well. An output method will only take data from the engine and push that out to some data sink. So could be writing it to a file, could be pushing out over the network, over industrial communication protocol, what have you. We have to tell the templates which one of these methods a particular channel is supposed to go to. Is it a input to the engine? Is it a processing parameter from the engine to a processing method? Is it a processing result from a processing method to the engine? Or is it output data from the engine out to the outside world? In the case of an LED module, the correct choice here should be output data, because what we're going to be doing with this module is pushing data, the LED state, out to the outside world. It only takes data from the engine. It never produces data to the engine. That means it's an output module. It being an output module also means it's guaranteed to run after all inputs and processing methods have already executed. It's the right place to put it. So I set those as output data. If we go over to execution options, this is where we get to set how many of these modules can be instantiated on a given system. For things like a PID module, you might want to have a whole bunch of PIDs, and that's fine. But it doesn't really make sense to have more than one LED controller when there's just one LED. In fact, it's the canonical example of something you only want one of. So instead of the default, which allows an unlimited number, let's set it to 1 so we only get one LED. Hit finish, and what LabVIEW will start doing for you is scripting out a complete project that contains each of the 3 classes that we mentioned, the runtime, the editor, and the configuration classes, as well as a library of tests you can run to make sure that everything is working correctly. And there we are, popped up a bunch of pre-scripted VIs for us. Close those out, and you can see in the resulting project we have all those classes in the test library I mentioned. If you remember how much code there was in the shipping LED module, If you look here, we have almost all of it already done. All of the plumbing necessary to get a editor screen created, configure those channels, get that configuration information over to the target, initialize it on the target, and make it available to your input, processing, or output functions is already done. There are a few places you might want to customize. You're not going to need to touch the configuration class. Nice thing about the static channel module is it's static. We can script out everything that we need here. For the editor node, the most common thing that you're going to want to change is what gets displayed in the tree control. So if you remember, we added the LED module, it said LED. Well, the default behavior of this function is that it will take the name of the class and use that as the display name. So this one would be called Demo LED, because that's the name of the class. We also have a glyph that gets displayed next to the module in the tree. If you want to have a more interesting glyph than the default, you can provide your own PNG file and put it in the same directory as the editor node, and just tell us the name. We'll take care of the rest. Another neat trick that you can do is you can actually use all of LabVIEW's built-in glyphs that are used in the icon editor and just reference them by name. We pull all of those into our glyph database, and you can reference them directly and cheat a little bit. For example, the directory where LabVIEW stores those glyphs is in your Documents, LabVIEW Data, Glyphs folder. And a neat thing about this is that, say we wanted to use an LED glyph, there's already one in there. No fun icon editing required. I can just go in here, say I want led.png. It's going to look through the database of known glyphs, which by default includes everything in here, or anything that you put next to your editor class. So I'm just going to save that. That's the only thing I changed, was the name of the glyph I wanted. Close it. The other thing that I obviously need to fill in here is what I want this module to do at runtime. Our scripting template will automatically generate wrapper functions that are necessary to get you all the configured data channels to your input, output, and process methods. These are the wrappers that are provided. So for example, our output method, this is what manages the conversion of data from the engine into the specific cluster that we defined when we created our module. We then provide you with a user output, or user process, or user input for the other overrides. This is where you fill in the blanks for your logic. Here's the current value of all of the channels you've configured to be output channels. They go to your output method. And here we fill in the blanks to decide what to do with them. If you have a LED logic VI that you've already created that just contains the logic necessary to decide whether it's time to blink the LED, blinking the LED becomes as simple as we can just unbundle the 3 pieces of data here that we need. Tell how many blinks that we want. And then we'll just add a little bit of Boolean logic to handle the enable and the color case, just basically select what we want to do. And in the interest of not having this be an hour-long video, I'm just going to skip to the part where we get to that point. And through the magic of video editing, we've got a completed VI. A few things to note here that are very important when developing packages for real-time systems. To blink the real-time LED on a compact Rio target, we have to call a function called, amusingly enough, RTLEDs, that's only available if you're targeted to an RT target. It's not available for Windows. That's why we said we don't want this to run on Windows. For this to work properly, what we need to do is add a conditional disable structure around any code that can't execute on the Windows target. So here it's based on if the target is RT, we can call the RTLEDs function. If we're on Windows, we do nothing. Let's make sure we connect our errors here. If we want to add in that function the way that you do it, to get that RTLEDs function in place, we can cheat a little bit. You can add a compact Rio target to your project, retarget this one VI from my computer over to the my computer target, over to the RT compact Rio target, at which point it can find it. That's how I dropped it down in the first place, is I switched it over to be on the compact Rio target, add the function which is available in the RT Utilities palette for RTLEDs. It's not there in Windows. And drop it in a conditional disable structure that only runs when we're on RT. Why did we bother with this? Well, the reason we did that is because typically decaf modules are built and distributed with VI Package Manager. VI Package Manager compiles all VIs for Windows when building the package. Meaning if the VI is broken on Windows, the package will be broken. So we add the conditional disable structure to make the package happy. It also makes sure that there's no runtime errors if this module ever gets loaded on the wrong target. It just won't do anything. Another important thing to note here is rather than calling the RTLEDs function every single iteration, every single time the output function gets called, we put it in a case structure such that it only gets called if the state of the LED is different than what it used to be. This prevents using excessive CPU resources on operations that have no end effect. One of the key considerations when building a decaf module is anything that you put into your runtime class should be built to run as fast as it possibly can. So try to keep your code as lean and mean as possible. We've done that with all the modules that come from National Instruments. You can feel free to look at our source code for examples of how to do that. So at this point, I'm just going to target this guy back to my computer. Make sure we save everything. Save it all. And we can, of course, run a couple of tests to make sure that everything worked properly. I always like to do that to make sure that I didn't accidentally break anything. One of the key tests to make sure of is the serialization test, as well as the cross-linking tests. These take care of the most common errors when building modules. But as you can see, when working with the static channel module, there's not a whole lot of errors that come into play. That becomes much more important when we give you the freedom to make a dynamic channel module, which we'll look at in the next video in our series. There are a few optional overrides that you can implement to customize the behavior of the module. There's one left that we need to do for LED. If you remember, we weren't allowed to try and run an LED module on Windows. We have to tell decaf that that's the case. The way that you do that is you go to the configuration class, go to customize, properties. We've already scripted out the necessary functions to get the supported targets. Let's open this. By default, it's going to support any target. So we get everything. What you can do is instead of getting absolutely everything, which by default has the full list of options, you can simply take off Windows, Mac, Linux, etc., such that, for example, it is only allowable on Linux RT ARM or Linux RT x64 targets, which is what I'm going to do here. Let's create a constant on here. I will allow this to run on the two Linux RT type targets. I'll make it a little bigger just so we can see it. There we are. And clean it up. At this point, if I save that, now I have a decaf module that will blink my LEDs, that will be called demo LED in the project, It will only allow one instance and can only be created on targets of type Linux RT. In order to actually create and package the module, you'll need to create a VI package build specification. If you've never done this before, take a look at our video on packaging decaf modules. We expect that to get published soon. So to summarize what you need to do to modify the static module template to create your module, here's a handy guide. For your configuration class, you have the optional ability to select the module options, so number of instances, the allowable targets like we did with the LED module. You can also update validate.vi with validation rules for your module's configuration. For example, if you want the editor to display a big red X over the module if a user has entered something that's incorrect for your module, the rules to generate that big red X over the module are located in validate.vi. You can also update getDefaultErrorList.vi. This provides the default set of errors that this module can classify. Decaf has the ability to take different actions depending on the classification of an error generated by a module. If you know that you want to ignore some errors from your module, or set them to be a low priority error, you should define them here. On the editor class, there's virtually nothing you need to do here. Almost all of it's provided by the template and the parent class that the template is based on. For this, all that you'll really want to do is select the module glyph like we did with the LEDs. Most of your work is going to be in the runtime class. This is where you'll need to implement the user input, user process, and/or the user output VIs with custom logic, depending on what type of module you're creating. If, like the LED module, all you have are outputs, then you only need to modify the user output VI. You can leave all the rest as they are with the template, and it'll work just fine. To learn more, please visit our pages at ni.com/decaf, or take a look at our source code and collaborate with us directly in the development at github.com/lavu-decaf. Thank you for your time.